H2S2O7. H2S2O7, pyrosulfuric acid. How will you draw? 2 sulfurs. Okay. 2 hydrogens, therefore 2 OH groups, distribute equally, 2 OH. Therefore, 7 oxygens, you have already used 2 of them, you are left with 5. 5, distribute equally, 1, 2, 3, 4, 5. Oxygen forms 2 bonds. H2S2O7. 2 sulfurs, 4 oxygens, 2 OH. H2S2O7. Now, H3PO3. H3PO3. It is slightly out of the ordinary. You can say it's an exception to what? If you have 3 hydrogens, 3 OH groups, number of OH groups is equal to number of hydrogens present. And you will know why that is an exception also. 1 phosphorus, 3 OH. If you write like this is not correct. What's wrong with this? So, here phosphorus is left with a pair of unused electrons, lone pair. And you know this lone pair will cause repulsion to the bond pairs. And the structure which would have been planar becomes pyramidal. If the lone pair is not there, the 3 bonds, it would have happily been planar, like boron trifluoride, planar. But molecules like NH3, they are not planar. Why? Because of the lone pair, it's not planar. The 3, they are not like this, they are like this, planar, pyramidal. Now, H3PO3. So, what solution we have for this problem? Try to avoid lone pairs. That's what the instruction says. How to avoid? You see that one of the oxygens is directly bonded, so that even the pair of electrons which is not used, lone pair, is also put in bonding. P double bond O. 2 OH only are directly attached and 1 hydrogen. Here these 2 atoms, oxygen and hydrogen, they are not directly bonded. They are not bonded with each other, but they are bonded to phosphorus. Therefore, you have 3 hydrogens, H3PO3, but only 2 OH groups. The 3rd hydrogen is not bonded to oxygen. The 3rd hydrogen is directly bonded to phosphorus. So, we said it's an exception. It's not so. It's not so. It is another important generalization. Try to avoid lone pairs as far as possible. H2S2O5. A very peculiar case, H2S2O5. Very interesting as well. You apply the generalization. 2 sulfurs, 2 OH distribute equally. 2 hydrogens, 2 OH distribute equally. You have 5 oxygens. 1, 2. You already used 2 of them. 3. 3rd one in the middle. You would like to write the structure like this. But this again is not correct. Why? On both these sulfurs, you have a pair of unused electrons. Both these sulfurs. How come? Sulfur has 6 electrons, 1, 2, 3, 4. It's using only 4 bonds. It's using only 4 electrons in bonding. So, a pair remains. So, 2 sulfurs, 2 OH groups, the remaining 3. Therefore, what we shall do is, you just readjust the oxygen in such a way that, look here, H2S2O5 is what we are discussing. H2S2O5. 2 sulfurs, OH, double bond O. Let this oxygen also form a So, if you write like this, you have two lone pairs. Both the sulfurs have a lone pair. Here at least one sulfur is rid of the lone pair. So, what is the consolation? The consolation is at least one sulfur got rid of lone pair. What is that our instruction say? Try to avoid lone pairs as far as possible. At least one sulfur got rid of lone pair. One sulfur got rid of lone pair. Okay, that is the consolation. So, lone pairs are avoided. Lone pairs are avoided even at the cost of symmetry. So, had the oxygen been at the center, had the oxygen been bridging oxygen, it would have been a symmetric structure. But look here, lone pairs are avoided even at the cost of symmetry. Okay, symmetry is lost, never worry. Avoiding lone pairs is more important. You might as well get a question, why is this oxygen not directly bonded so that the other lone pair also gets rid of? That's not possible, because if you want this oxygen also to be bonded directly, like this, here hydrogen is directly bonded to sulfur. Only first two bonds are offered for hydrogen. For example, sulfur has two unpaired electrons and two pairs, and hydrogens are offered only the first two unpaired electrons. It is the sixth bond is not offered to hydrogen. For the sake of hydrogen, the pairs of electrons are not broken. It's okay for oxygen, but not for less electronegative element like hydrogen. So, how to draw any structure? We have discussed how to draw any structure. That includes the structures of all SO3, NO2, XeO3, ClO2, among other things. These are the oxides of our present groups. Oxides, hydrates, oxyacids, halides, you have learned. And what is the question that is specific to? And there is one more question on molecules. Suppose SO3 or XeO3. Apart from structure, what will be asked is the shape and hybridization. Shape and hybridization we have discussed in chemical one. I will just remind you, I will just bring back those things. If you are watching the lectures in an order, periodic table, chemical bond, perhaps you don't require. But maybe if you maintain some gap between the lectures, it's my duty to remind you. The possible questions on SO3 or SO2 or the oxidation state +6, the shape, the structure in which you have 3 sigma and 3 pi bonds, 3 sigma and 3 pi bonds. Oxidation state of sulfur is +6. How to find? Yes, of course, we have a procedure. The oxidation state of sulfur +6. Just as you have seen a procedure for drawing a structure. How to draw a structure? How to find oxidation state? 1, 2, 3 sigma, 3 pi bonds, 3. The shape is trigonal planar. How do you know? 3 bond pairs and no lone pairs. 3 bond pairs. So, how to determine the shape? That's another procedure. Structure, oxidation state, shape. Hybridization, sp2. So, and 2 d pi p pi bonds in SO3 have 1 d pi p pi bond and 2 d pi p pi bonds. How can we find d pi p pi? There is a procedure for that also. Everything, there is a simple procedure, 1 or 2 step procedure. Stick to that. Right. Hybridization. V plus M minus C plus A by 2. V is number of valence electrons. Of course, number of valence electrons of the central atom. I am only reminding you. We have discussed this in chemical bonding. Number of valence electrons of the central atom. M, forget oxygens. Even if you have 2, 3 oxygens, don't count them. Don't count them. C means cation, positive charge. A, negative charge. That's all. Formula appears to be very big, but its application is very simple. BeCl2. Beryllium valence electrons 2. 2 plus 2 by 2. Valence electrons of beryllium 2 and 2 chlorines. We consider chlorines. We don't consider oxygens only. Oxygens are not considered. You calculate all others. So, it's not a cation or it's not an anion. If it is a cation, you get positive charge. If it's an anion, you get a negative charge. It's not an ion. 2 plus 2 by 2, you got 2 sp. So, 2, 3, 2, 3, 4, etc. amounts to sp, sp2, sp3, etc. sp3d, sp3d2, d3. So, S, P and D, if necessary, involve all of them. Now, so I'll just write the formula again. V plus M minus C plus A by 2. Valence electrons of the central atom, monovalent atoms, positive charge, negative charge. SO4 2 minus 1 sulfur 6, sulfur 6 group 6. 4 oxygens 0. 6 plus 0 plus 2 by 2. 6 plus 0 plus 2 by 2. 8 by 2, 4. sp3. SO3. How will you calculate? 6 plus 0 by 2. I told you oxygens are ignored. Only monovalent atoms, those who form one bond only, are taken into account. 6 plus 0 by 2. 3 sp2. So, the hybridization of sulfur in SO3 is sp2. We are answering such a question. The hybridization of sulfur in SO4 2 minus is sp3. PCl4 plus. What is the hybridization of phosphorus in this ion? 5. Group number, valence electrons. 4 chlorines. Consider them. Only oxygens need not be considered. Oxygen, all others should be considered. 5 plus 4 minus 1 by 2. I told you positive charge should be subtracted, negative charge should be added. Positive plus comma, right. 5 plus 4 minus 1 by 2. 9 minus 1 by 2. 8 by 2, 4, once again sp3. That's about hybridization. Now, hybridization without formula. How to find hybridization without a formula? Go to the relevant excited state. Hybridization without using any formula. The logical method. Go to the relevant excited state. Leave as many pure orbitals as the number of pi bonds. Leave as many pure orbitals. Pure orbitals in the sense, s orbital is a pure orbital, s. P orbital is a pure orbital, d orbital is a pure orbital. But sp is a mixed, a hybrid orbital, sp, sp2. Where two letters are there, it is hybrid. Only one letter. Leave as many pure orbitals as the number of pi bonds. Mix all others. Now, let us try to apply this for SO3. You have seen this is a simple two-step procedure. Just two steps. SO3. Sulfur. 3 sigma bonds, 3 pi bonds. How can you know? 3 sigma, 3 pi. Total of 6 bonds. XOM, M sigma bonds and M pi bonds. Because each oxygen forms 1 sigma and 1 pi. If you have M oxygens, M sigma, M pi. Then XOM N minus M sigma M minus N pi. M sigma bonds and M minus N pi bonds, because N of them are not oxygens, they are O minuses, you know. XeO4, what can you say about it? 4 sigma 4 pi. How? You have 4 oxygens, 4 sigma 4 pi. What about SO4 2 minus? SO4 2 minus 4 sigma and 2 only are pi bonds. Why? Out of the 4 oxygens, 2 of them are minus. 4 oxygens, 2 of them are minus 2 pi. 4 sigma 2 pi. Now, SO3, since you already know it is 3 sigma 3 pi, total 6 bonds. What's important for me is the total number of bonds. A total of 6 bonds. Sulfur, the ground state electronic configuration goes like this: 3s2, 3px2, 3py1, 3pz1. 3s2, 3px2, 3py1, 3pz1. This is the ground state electronic configuration of sulfur. 3s2, 3px2, 3py1, 3pz1. 2, 2, 1, 1. Sulfur cannot form 6 bonds in this state. Cannot form 6 bonds in this state. Why? There are only 2 unpaired electrons. So, let us try to excite the electrons. First excited state. 3s2. I said go to the relevant excited state. Relevant in the sense until you get the required number of bonds. In the case of SO3, you know you require 3 sigma and 3 pi, a total of 6 bonds. So, 3 sigma, 3 pi. 2, 2, 1, 1, break this pair as well, 3s2. 3px1, 3py1, 3pz1. Look at this pair of electrons, is no longer there. The pair has been broken, and take that to 3D, the next level, 3D1. First excited state. Second excited state. Break this pair also, 3s2. 3s1, 3px1, 3py1, 3pz1, 3d1 and 3d1 again. What happened? This 3s is once again broken. This pair is also. So, you now have 6 unpaired electrons. 6 unpaired electrons. You require 3 pi bonds. Pi bonds are formed by pure orbitals only. Pi bonds are formed by pure. Hybrid orbitals cannot be used for the formation of a pi bond. So, 3 pi. Leave these 3. Mix all others. You have sp2. sp2 hybridization. 3 pure orbitals. 3 pure orbitals meant for 3 pi bonds. 3 pure orbitals meant for 3 pi bonds. 3p Z1, 3d1, 3d1. 3 pure orbitals meant for 3 pi bonds. So, what happened here? Sulfur has 3 pi bonds. Sulfur is forming 3 pi bonds in SO3, out of which 2 are involving D. 2 bonds, D is involved, and that is called a D pi P pi bond. So, out of the 3 pi bonds, look here, out of the 3 pi bonds, 2 are with the involvement of D. So, you have one P pi bond. What do you mean by a P pi bond? P orbital, look here, P orbital of sulfur and P orbital of oxygen, P pi. 2 D pi P pi bonds. 1 P pi, 2 D pi P pi. D pi P pi bonds. So, if you just write down the electronic configuration in the required excited state, required, if you want 6 unpaired electrons, 6, 4, 4. I will give you a hint here. All the pi bonds of, don't forget, all the pi bonds of chlorine, bromine, iodine and xenon, chlorine, bromine, iodine and xenon are D pi P pi bonds only. D pi P pi only. All the pi bonds. Only for sulfur and phosphorus you may have to check. XeO3, what do you know about that? 3 sigma, 3 pi, and all 3 D pi P pi. All the 3 pi bonds are D pi P pi. What is a D pi P pi bond? D orbital of the central atom. I repeat, D orbital of the central atom and P orbital of the terminal atom. D pi P pi. It is a D orbital of sulfur and the P orbital of oxygen. A D pi P pi bond. Usually P pi P pi, this is a special case where D pi P pi bond is involved. D pi P pi. So, we now have hybridization, D pi P pi bonds, everything. Now, shape of how do you find the shape of a molecule? It depends on the number of bond pairs, number of terminal atoms, to be more precise. Number of bond pairs means number of terminal atoms, number of guest atoms. Don't hesitate to use such a language. Guest atoms, the terminal, the incoming, the guest. Central atom is the host. In sulfur trioxide, sulfur is hosting 3 oxygens. So 3 oxygens are guests, 1 sulfur is the host. Now, number of bond pairs and simply number of lone pairs. Shape of a molecule depends on number of bond pairs and number of lone pairs. And you may have to memorize that list. 2, 0. What is this 2, 0? 2, 0. 2 bond pair, no lone pair. This is called linear. 2, 0. Let me give you 1 or 2 examples. BeCl2, 1 beryllium, 2 chlorines. That's all. BeCl2. And there is no lone pair. How to find the number of lone pairs? Number of lone pairs. That again is not. So, you have to memorize this list. 2, 0, 2, 1, 2, 2, 2, 3, the whole lot. 2 bond pairs, 0 lone pairs, 2, 1, 2, 1, 2, 0, 2, 1, 2, 2, 2, 3, etc. I can quote examples. BeCl2, no lone pair. SnCl2, there is a lone pair. 2 1. Example of 2 1. 2 chlorines and 1 lone pair. 2 2 H2O. 2 bond pairs and 2 lone pairs. 2 3. Too many lone pairs. What is that? What are the number of bond pairs and number of lone pairs? Shape depends precisely on this. 2 3. XEF2. So the procedures we are learning, they are not particular to any particular compound or any particular group. Here you are seeing compounds on second group, fourth group, sixth group, 0 group, the entire P block. The entire P block, hybridization, lone pairs, shape, follow. So 2 3 is again linear. 2 3 is 2 3, 3 lone pairs. 1 2 3. XEF2. 2 0 2 0 2 0 linear, 2 1 bent, 2 2 V shape, like that. 2 0 2 1 2 2 2 3, because there are too many lone pairs, that finally the molecule assumes a linear shape. 2 3. Like that you can have 3 0 3 1 3 2. Trigonal planar, pyramidal, T shape. Boron trifluoride. So how to find lone pairs? Number of lone pairs is equal to, once again, number of valence electrons of the central atom. Of course, of course, of course. Don't make me repeat that every time. Number of valence electrons of the central atom. Only central atom is important. Number of valence electrons minus number of electrons used in bonding. It's very strange. A bond involves one of your electron, or sometimes 2 of your electrons, or none of your electrons. A bond, 2 atoms may share. Here X and Y are using 1 electron each. Of course, a normal covalent bond. Both X and Y are sharing. As another bond where X is donating to Y. Here X is spending 2 electrons, Y is not spending anything. In fact, X is enjoying that, enjoying the electrons of X. So Y is forming a bond at no cost. X is losing 2 electrons. Here X and Y are losing 1 electron each. So X and Y, they are using, so number of valence electrons. So I am not saying it is number of bonds, because a bond does not guarantee your electron. You may form a bond in which 1 of your electron is used, or 2 are used, or 0 are used. So 2 0 linear, 2 1 bent. If necessary, you have to go through this lesson 2 3 times. I mean, to memorize. 2 0 linear, 2 1 bent, 2 2 V shape, 2 3 linear again, 3 0 trigonal planar, 3 1 3 1 3 1 pyramidal, 3 2 T shape, 4 0 4 1 4 2 4 0 4 1 4 2. 4 0 is tetrahedral. 4 1 is distorted tetrahedral. Distorted tetrahedral. Also called seesaw. And 4 2 square planar. I am not making a lengthy list because the list is available wherever you want. Tetrahedral 4 0. Methane, no lone pair. How do you know? 4 minus 4 by 2. 4 minus 4 by 2. SF4, 4 bond pair, 1 lone pair. How do you know? Sulfur 6th group. I tell you the group number is very, very, very important. 6 minus 4 by 2. 4 minus 4 by 2. SF4, 4 minus 4 by 2. XEF4. So, you should call it 4 and you don't see any lone pair here. 0, 4, 0. 4, 1, 4, 2. You can actually see the lone pairs. 4, 0, 4, 1, 4, 2. Square planar. Like that 5, 0, 5, 1, 6, 0, 6, 1, 7, 0. Just go through any list and get to the shape. So, what is that we have learnt until now? You have learnt 11 properties about atoms. If not properties, 11 facts about atoms. Their atomic numbers. How to find the atomic numbers of all elements starting with the first one. Starting with nitrogen, how to go towards bismuth to the end. So, how to get atomic numbers, symbols, names, so many things. Be thorough with these things. And we will have to apply these things only at a later stage. And regarding molecules, you have known the structure, you have known the hybridization, you have known the shape, like that. We just have to see whether somebody is acidic or basic. SO2 is an acidic oxide. How? There is a procedure for that. NO2 is paramagnetic. There is a procedure for that. I can say SO3 is more acidic than P4O10. How? There is a procedure for that. So, for all these statements, there is a strong reason, strong logic behind that. We have to learn that. Distorted tetrahedral, square planar, 5, 0, 5, 1, 5, 2, 5, 0, trigonal bipyramidal, PCl5. Trigonal bipyramidal, 5 bond pairs, no lone pairs. 5, 0. I need not write that in so many words. Do you see any lone pair here? You don't. Therefore, it's 5, 0. So, the moment I write SF6, you have to say 6, 0. 6, 0. You don't see any lone pair. XEF6, 6, 1. IF7, 7, 0. Why 0? You don't see any. So, when you don't see any lone pair, you call 0. And when you indeed find lone pairs, you count them. 4, 2, 4, 1, 7, 0, 4, 1. So, we have discussed some of the properties of elements and some of the properties of, and we will discuss more.